To see about the architecture of 8085 microprocessor. Completion of this lesson, the students can able to understand 85 architectures, general purpose registers, flag registers, instruction registers, interrupt control signals, serial I/O control signals, timing and control unit. This is the architecture block diagram of 8085 microprocessor. It contains the following. They are interrupt control, serial I/O control signals, accumulator, temporary registers, flag registers which are also called as flip-flops, arithmetic and logic unit, then instruction register, instruction decoders, then register select signals, stack pointer, program counter, incrementer and decrementer, then the timing and control unit as well as address buffer, address slash data buffer. So first we are going to see about general purpose registers. So what are general purpose registers? Register A, register B, register C, register D, register E, register H and L. They are together called as general purpose registers. Each register, it has the capacity to store 8 bits of information. 8 bits of information. So here A is also called as accumulator register, which I have indicated here, and B register is 8 bit and C register is also 8 bit. So each register has the capacity to store 8 bit of information, and when you want to deal with 16-bit data, you can get the registers as pairs. B can be paired with C register, D can be paired with E register, H can be paired with L register. HL registers are the registers which is used by memory. The main purpose of HL register to locate the address of the microprocessor. Apart from these general purpose registers, we have two special purpose registers, so which are called as SPR, which uses stack pointer and program counter. So these are some of the general purpose registers, and stack pointer and program counter, they are called as special purpose registers. Each register, it has the capacity to store 16 bit of information. And we have one more register which is called as temporary register, where the user cannot modify any data under the temporary register. The temporary registers are used by microprocessor alone. So also W and Z are also called as temporary register, which can hold 8 bits of information. If the microprocessor needs to make use of 16-bit information, temporary register information, it will be taking W register and Z register for the purpose of storing the information temporarily. So next to the stack pointer and program counter, we have incrementer and decrementer. Incrementer and decrementer, it increments and decrements the values by +1 or -1. After that, you have address buffer and data slash address buffer. So address buffer is the one which points the higher order addresses from A8 to A15, and here data and address, they both can make use of the lower order addresses, or it can be written as AD0 to AD7 multiplexed. The address and data, they are multiplexed together. So data can also make use of the address buffer, and the range of data and address buffer, it may vary according to lower order address and as well as higher order address. So as I said, the special function, there are two special function registers. The first one is called as program counter. It is a 16-bit program counter, and also you have stack pointer. It is also a 16-bit stack pointer. So program counter, what do you mean by program counter? A program counter is the one which stores the address of the next instruction to be executed. Okay, so what does the program counter do? It keeps track of the memory address of the instruction that are being executed by the microprocessor, and and the memory address of the next instruction that is going to be executed. For example, if the microprocessor is executing the address 2004, what would be the next address that should be executed by the microprocessor? That can be 2005. So the program counter is the one which keeps track of the address to be executed. Okay, so currently the microprocessor is working with the 2004 address. The program counter will be pointing the next address that should be executed. Okay, so that's what it is called as. It keeps track of the memory address of the instruction that are being executed by the microprocessor and the memory address of the next instruction that is going to be executed. So this is the job of program counter. So next we can see about the stack pointer. So stack pointer is also 16-bit pointer. So it maintains the address of the last byte that is entered into the stack. Okay, so stack, it has a pool of address. It maintains the address of the last byte which is entered into the stack. For example, let's say the address to be 2004, which is lastly used by the microprocessor, right? So it maintains, or it points to the address of the last byte entered into the stack. So each time when the data is loaded into the stack, so when the data is loaded into the stack, what happens? The stack is decremented. The stack pointer is decremented. When the data is retrieved from the stack pointer gets incremented. So when a data or when an address is loaded into the stack pointer gets decremented, or when the data is retrieved from the stack pointer will be incremented. Okay, so differentiate between the program counter and the stack pointer. Program counter, it always keeps tracks of the address of the next instruction to be executed, whereas the stack pointer will be locating or pointing to the current address of the last byte. So when the data is being entered, what happens? The address is being entered, the stack pointer is decremented, or when the address is retrieved from the stack, the pointer gets incremented. So next we are going to see about flag registers. So flag registers are also called as flag flip-flops, or it is also called as status registers. Okay, so there are certain flag registers which are seen in 8085 microprocessor. The first one is called as sign flag or negative flag. The second flag register is carry flag, and the next one is auxiliary carry flag, and the next one is parity flag, and then we have zero flag. So these are the 5 flags used by 8085 microprocessor when the arithmetic or logical operation results in negative sign, negative flag is set. Otherwise, it is reset. When the arithmetic or logical operation results in carry, carry flag is set. Similarly, when the arithmetic or logical operation results in auxiliary carry flag is set, otherwise it is reset. And when the arithmetic operation results in even number of ones, the parity flag is set, otherwise it is reset. Similarly, when the arithmetic operation results in 0, zero flag is set, otherwise it is reset. So let's see some of the examples stating this status registers. Let's start from the sign flag. I have taken two numbers, two 4-bit numbers for giving an example. So when you subtract these two numbers, the result will be, it will be ending with borrow, because the last digit, the MSB, the last digit is 0. So this will be, it becomes 1 0. So 1 0 minus 1 results in 1, and we are having a borrow condition, or this one can be written as minus also. It is resulting as negative. So during such conditions, the sign flag will be set to 1. Okay, only during the condition of getting the borrow, the sign flag will be set as 1. Otherwise, in the case of normal situation, like for example, when you subtract these two things, it results in 0, right? 1 minus 1 is 0. So during this kind of operation, there is no way you are getting a borrow. So during this kind of operation, the sign flag will be 0. But the case of 0 flag, when the arithmetic operation results in 0, 0 flag will be, that is Z, will be set as 1, because the arithmetic and logical operation is resulting 0. So 0 flag will be set, but the case of negative flag will be 0. Okay, so we have learned about sign flag and 0 flag. The next thing is about carry flag. So carry flag is set when the arithmetic and logical operation results in a carry. I'm giving an example for this by adding two numbers. So what happens if I add these two numbers? This becomes 1. Sorry. So here it is 1. This one becomes 1 again. 1, 1, 1. So 3 times 1, adding 1, it gives you a carry which is 1. So these two arithmetic operations resulted in a carry. So for this, the carry flag is set. Okay. So now let's see the case of auxiliary carry flag. Under the case of auxiliary carry flag, there will be a transition when we are dealing with 8 number of bits. The best example can be given by assuming 8 number of bits. Okay. So for our simplicity, I have taken 4 bits. So now for good explanation, I'm going to take 8 bits. Let's say the bits to be like this. So while adding these two datas, it will result in 1 1 is 0 1 0 1 0 1 and again 1 1 0 1 0 1 0 1 0, again you have a carry. Okay. So what I have did, I have dealt with 8-bit number. So the datas are represented from LSB to MSB starting from D0 to D7, right? So when you see, if there is a carry from D3, if I say this as D0, then this will be D1, D2, D3, and this will be D4, D5 and D6, right? So if there is a transition of carry from D3 to D4, it is happening, right? So 1 1 1, it becomes 1 1, right? So 1, and the carry is being forwarded here, so it becomes what? 1 and 1, right? So if there is a transition of carry from D3 to D4, auxiliary carry flag is set. Otherwise, it is reset. In the case of not carry forwarding to D4, auxiliary carry flag will be 0. In the case of forwarding the carry to D4 number, auxiliary carry flag will be set. So in the case, you can see again the addition operation resulted in carry also. So what are the flags gets affected? The auxiliary carry flag, it becomes 1, and also the carry flag will also becomes 1. Is it clear? So the next flag is parity flag. As I said, when the arithmetic operation results in even number of ones, parity flag is set, otherwise it is reset. So let's say for example, if you have the parity 8 bits, 8-bit number like this, right? So just count the number of ones. How many number of ones are there? It is 6 number of ones, right? So that means even number of ones. 6 is an even number, right? So even number of ones, that means the parity flag will be 1. Otherwise, if it doesn't result with 6 number of, that means even number of ones, the parity flag becomes 0. Another example, let's say count the number of ones. It is only 3. How many number of ones are there? 3 numbers of ones, right? So that means in this case the parity flag is not set, that is reset. Okay, so that's all about flag registers. The next is about the instruction registers. These registers usually carry the information about the instructions or programs. The instructions are fetched from the memory and are directed to the instruction register. So after the instructions are seen in the instruction register, it is being decoded with the help of instruction decoder, which decodes the informations present in the instruction register for further processing. Next, we are going to see about interrupt control signals. So before we go for interrupt control signals, we should get an idea about what is this interrupt. So interrupt, it can be a signal or a piece of program that requires the attention of the microprocessor. So what happens as soon as an interrupt request is being given to the microprocessor stops executing the current program, and it will be allowing the interrupt to respond to the signal. Right, it stops executing the current program and it will look for the signal which is being interrupted. Right, so for this kind of action we are having certain signals. It starts from interrupt request, interrupt request signal. The next one is interrupt acknowledgement signal, which is followed by four signals. Out of these four signals, we are using three maskable signal, and the trap signal is a non-maskable signal. Okay, so maskable in sense the designer or the programmer can able to change the information. Non-maskable in sense the designer or the programmer, they cannot make changes with this signal. And out of these four signals, the trap signal is given the first priority, followed by the RST signals. Here RST 7.5 is given the next priority after the trap signal, and then the least, following this order, the least priority is given to RST 5.5. Okay, so we have interrupt request signal to make a request to the microprocessor whether the microprocessor can be interrupted. So as soon as the microprocessor receives the interrupt request signal, it sends an acknowledgement to the one which is interrupting. So most of the signals which are supposed to interrupt can be from IO signals, that is IO peripherals. So IO peripherals or memory devices, they can interrupt the microprocessor by sending interrupt request signal. So as soon as the microprocessor receives the interrupt request signal, it stops executing the main program. It stores the address in program counter or stack pointer, and then it looks for the signal which is interrupting it. So before it looks for the signal which is interrupted, it sends the interrupt acknowledgement signal back to the interrupt control. So now the IO signal can be connected to either any one of the RST signals. We have three RST signals. Out of 3 RST signals, the first priority is given to the 7.5 signal, which is followed by 6.5, and the least priority is given to the RST 5.5 signal. So here these RST signals are maskable signals, and trap signal, there is one more signal which is called as trap signal, which is non-maskable signal, which is the most priority is being given to the trap signal. The next is about serial I/O signals. So there are two serial I/O signals. They are used for serial communications. They are SID and SOD. SID, it stands for serial input data line, and SOD, it stands for serial output data line. So SID is loaded into the accumulator whenever a RIM instruction is being executed. Okay, so RIM is nothing but it is called as read interrupt mask. Similarly, we have SOD, which can be set or reset as specified from the instruction SAM. That means set interrupt mask. So based upon RIM instruction and SIM instruction, the result of SID, SOD may vary. So the next is about timing and control unit. So under the timing and control unit, we have X1 and X2. They are clock signals. They are clock signals which is generated by using crystal oscillator, where these two pins are used to set the frequency of internal clock generator, and it is usually divided by 2. The frequency is internally divided by 2. Okay, so these are X1 and X2 are the signals which are used to set the frequency for the internal clock generator. Usually it is divided by 2. So the next signal is called as clock out signal. This signal is used as a system clock for the devices connected with the microprocessor. Okay, so all the devices are synchronized using the clock out signal, because the clock out signal is used as a system clock. So the next signal is called as ready signal, which indicates the device is ready to either send or receive the data. Okay, so it indicates the device is ready to send or receive the data. The next signal is the read bar and write bar signals. So here the read bar signal is the one where the signal can read the information. When the signal is low, the signal can read the information either from IO device or from memory device. Similarly, the signal indicates for the data, for the write signal, it indicates the data on the data bus to be written into the memory or IO location. The read signal, it indicates the data which is from the IO or memory device should be read to or from the microprocessor, or the write signal, it indicates the data should be written to the IO or it should be written to the memory devices. If the signal is low, that means it is working for IO or memory device. If the signal is high, that means it is working for the microprocessor. So RD is used to read the signal, WR is used to write the signal. So the next signal is called as address latch enable signal, address latch enable signal, which is used to indicate a kind of pulse when a new operation is started by the microprocessor. The pulse goes high. When the pulse goes high, it indicates the address. When the pulse goes low, it indicates the data. So when the pulse goes high, it indicates the address, or when the pulse goes low, it indicates the data. So the next two signals are S0 and S1, which is used to identify the type of operation. What the microprocessor is currently doing. So S0 and S1 are the signals which is used to indicate the type of operation what the microprocessor is currently doing on it. The next signal is IO slash M bar. IO slash M bar, it stands for input output memory bar. When IO slash M bar is logic 0, it represents the address sent out by the processor is for addressing a memory location. Whereas when IO slash M bar is equal to 1, that means the address sent out by the processor is for addressing the IO ports. There are two signals which are called as hold signal and HLDA. Hold and HL, it stands for hold acknowledgement. A stands for acknowledgement. So hold signal, it is used to indicate another master is requesting the use of address or data bus. Okay, so HLDA is the hold acknowledgement signal. It indicates the CPU has received hold signal and it is allowing to make use of address and database. Okay, so hold and hold acknowledgement are two signals where other master devices will be making use of it, and hold is received and hold acknowledgement is there, which is being saying that CPU has received the signal and it is ready to send the address and buses along with it. There are another two signals. They are reset in and reset out signals. The signal is used to reset the microprocessor by setting the program counter to 0. The program counter will be 0, and the signal is used to reset the microprocessor by setting it to 1. Reset in is used to reset the microprocessor by setting the program counter to 0, and reset out is used to reset the connected devices when the microprocessor is resetted. That's all about architecture of 8085. Thank you everyone.